Tonight, we're going to explore a question that sounds simple but turns out to be one of the most profound and disorienting puzzles in all of physics. What if time stopped? Not slowed down, not stretched in the way Einstein showed. It stretches near massive objects or at high speeds, not paused like a video with the freeze frame button pressed. Stopped. Completely, absolutely, everywhere, all at once. Here is the first problem. The question already contains an assumption that physics says cannot be true. When we ask, what if time stopped? We are imagining a universe in which time stops and then, presumably, starts again. We are imagining a before and an after. We are imagining a duration of stopping. We are imagining that there is some external clock against which we could measure the period of temporal cessation. But there is no external clock. There is no outside of time. Time is not a river flowing through an independent landscape where you could dam it and watch the water pile up. Time is part of the structure of the universe itself. It is woven into the fabric of space-time so completely that the question of what happens when time stops is not like asking what happens when a car stops. It is like asking what happens when the road stops existing while the car is still on it. And yet the question is not meaningless, because physics does have things to say about time, about what it is, about where it comes from, about whether it is fundamental or emergent, about the arrow of time and why it points only forward, about whether time could, in any rigorous physical sense, stop, about what a universe would look like from which time had been subtracted. And when you follow those questions carefully, when you trace the implications through thermodynamics and quantum mechanics and general relativity and the philosophy of time, you discover something extraordinary. Time stopping is not a single coherent concept with a single answer. It is a cluster of related questions, each with its own profound answer. And those answers reveal things about the nature of the universe that most people have never considered. 7 things that physics reveals when you ask seriously, what would happen if time stopped? Some of them will feel like science fiction. All of them are deeply grounded in the equations that govern everything. Before we get started, if these questions about the nature of time itself are the kind of questions that stay with you, that surface at odd moments and refuse to be dismissed, hit like or subscribe. It helps us reach more people who want to think about things like this. Now let's begin. The year is 1905. Albert Einstein, working as a patent examiner in Bern, Switzerland, publishes 3 papers in a single year that each would individually have been sufficient to establish a scientific legacy. One of them, the paper on special relativity, contains something that nobody had anticipated. A mathematical consequence of taking seriously the constancy of the speed of light in all reference frames is that time is not universal. There is no single clock ticking at the same rate for every observer in the universe. Time is relative. It depends on the state of motion of the observer, on their velocity relative to other observers, on their position in a gravitational field. 2 clocks that are perfectly synchronized and separated, one sent on a fast journey and one kept stationary, will show different times when they are brought back together. This is not a measurement error. It is not an illusion caused by signal delays. It is a real physical difference in the amount of time that has elapsed for each clock. The clocks genuinely experienced different amounts of time. Time itself passed at different rates for them. Einstein's theory did not just tell us that time can go slow. It destroyed the idea of absolute time entirely. There is no universal now, no moment that is simultaneously the present for everyone, everywhere. Each observer has their own proper time, their own clock rate determined by their velocity and gravitational environment. The universe does not have a single temporal backbone that everything hangs on. Time is local, personal, frame-dependent, and this matters enormously for the question of what if time stopped, because Einstein's answer to that question, worked out in the equations of special and general relativity, is already partially given. Time does not have a uniform rate everywhere. Some clocks run faster, some slower. The question is not whether time can vary in its rate. It can and does. The question is whether it can stop entirely. Whether the rate can reach zero. The answer is both yes and no. And understanding why requires going deeper into what time actually is. The first revelation, time already stops for light. Here is something that most people encounter and then immediately file away without fully absorbing its implications. A photon, a particle of light, traveling through empty space at the speed of light, does not experience the passage of time. From the photon's perspective, in the precise sense that special relativity permits us to talk about a photon's perspective, no time passes between its emission and its absorption. The journey that took billions of years from our perspective happened in literally zero time from the photon's perspective. This is not poetry. This is a mathematical consequence of the Lorentz transformation, the equations that describe how time and space coordinates change between reference frames, moving at different velocities relative to each other. As an object's velocity approaches the speed of light, the rate at which time passes for that object, as measured by a stationary observer, approaches zero. The time dilation becomes infinite at exactly the speed of light. The time dilation is infinite. No time passes. Massive objects cannot reach the speed of light because doing so would require infinite energy. But photons are massless. They travel at exactly the speed of light, and for them, time has stopped in the most literal sense that special relativity allows. A photon emitted by a star 10 billion light-years away, detected by a telescope on Earth, has from its own reference frame traveled from emission to absorption instantaneously. The 10 billion years we see it cross took, from the photon's perspective, no time at all. It exists at both the moment of emission and the moment of absorption simultaneously, in the sense that no intervening duration separates them. This is time stopping. Not hypothetically, not theoretically. Actually, right now. For every photon traveling through the universe, time is stopped. The universe is filled with entities for which time does not pass. But here is why this does not feel dramatic. A photon cannot have experiences. It cannot observe its own timelessness. There is no consciousness riding along in the photon's reference frame to notice that time has stopped. The photon does not think, does not remember, does not plan, does not have any sense of before and after, because before and after require time. And for the photon, there is none. Time stopping, in the relativistic sense, removes experience. There is nothing it is like to be a timeless photon, because experience requires temporal structure, requires the difference between now and a moment ago, requires memory and anticipation. Strip time away, and you strip experience with it. This is the first thing physics tells us about stopped time. It already exists. It is already realized in the photon, and it means nothing to the thing experiencing it. Nothing in the richest possible sense of the word. The second revelation, near black holes, time nearly stops. General relativity extends Einstein's time dilation from velocity to gravity. Gravity is not a force, as Newton conceived it. Gravity is the curvature of space-time caused by mass and energy. And moving through curved space-time means moving through a region where time passes at different rates, depending on how deep you are in the gravitational well. At the surface of a neutron star, where gravity is so strong that the escape velocity is a substantial fraction of the speed of light, time passes noticeably more slowly than it does far from the star. An observer on the neutron star's surface would age more slowly than an observer far away. This is gravitational time dilation, and it has been measured on Earth. Between atomic atomic clocks at different altitudes. Clocks at the tops of mountains tick slightly faster than clocks at sea level. The difference is small, but measurable and real. Near a black hole, gravitational time dilation becomes extreme. As you approach the event horizon, the boundary from within which nothing can escape the black hole's gravity, time dilation increases without bound. For an observer watching from far away, someone falling toward a black hole appears to slow down as they approach the horizon, moving more and more slowly, their signals becoming more and more red-shifted until they appear to freeze at the horizon itself, a figure hanging motionless at the edge of eternity as their light becomes too faint and too red-shifted to see. From the falling observer's perspective, none of this is apparent. They do not feel anything special at the event horizon. They cross it in finite time by their own clock and continue falling toward the singularity. But from outside, they appear to stop at the horizon. Time appears to stop for them. They are frozen at the boundary. This is not just an appearance, in a precise mathematical sense. An infalling observer's world line reaches the event horizon only at infinite time in the coordinate system of a distant observer. The distant observer and the infalling observer have genuinely different temporal experiences of the same sequence of events. At the singularity itself, if general relativity is taken at face value without quantum corrections, the curvature of space-time becomes infinite. All matter, all energy, all information that has fallen and reaches a point of infinite density in finite proper time. The equations of general relativity break down at the singularity. They produce infinities that physics cannot handle. Something different happens there, something that requires a theory of quantum gravity to describe, and we do not yet have that theory. But the singularity represents, in some models, a point at which space-time itself ends, not just a place where density becomes extreme, a literal boundary of space-time, a point beyond which the concepts of space and time do not extend. If that is what a singularity is, then it is not a place where time stops. It is a place where time ends, where asking what happens next has no meaning, not because the question is hard, but because the question is like asking what is north of the North Pole. This singularity may be where time stops not as a pause, but as a terminus. The third revelation. Time has an arrow, but physics doesn't. Here is one of the deepest mysteries in all of science, and it bears directly on the question of stopped time. The fundamental laws of physics are, with one very minor exception, time-symmetric. The equations of electromagnetism, quantum mechanics, general relativity, the strong and weak nuclear forces, all of them work equally well running forward and backward in time. If you made a video of two billiard balls colliding and played it backward, there is nothing in the physics of the collision that would tell you which version was the real one. Both are allowed by the equations. Both conserve momentum. Both conserve energy. The laws of physics do not prefer one direction of time over the other, and yet time has a direction. You remember the past and not the future. Eggs break and do not unbreak. Heat flows from hot to cold and never spontaneously reverses. Stars burn out and do not spontaneously reignite. The universe grows more disordered over time and never more ordered. You were born and you will die, and this sequence never reverses. Why? If the laws of physics are time-symmetric, where does the arrow of time come from? The answer lies in thermodynamics and entropy. The second law of thermodynamics says entropy, the measure of disorder in a closed system, never decreases. It stays the same or increases. This law is statistical, not absolute. It is not that entropy decreasing is physically impossible. It is that entropy decreasing spontaneously would require an absurdly improbable arrangement of particles, so improbable that it has never happened in any system large enough to observe. The arrow of time, the direction from past to future, is the direction of increasing entropy. The past is different from the future because the past had lower entropy. The universe began in an extraordinarily low entropy state. The Big Bang was smooth smooth, uniform, organized. Every moment since, entropy has been increasing. The universe has been moving from order toward disorder, from structure toward chaos, from concentrated energy toward dispersed equilibrium. This is what time is at the thermodynamic level. Time is the direction of entropy increase. Past is where entropy was lower. Future is where entropy will be higher. Now, what does this say about stopping time? If time is the direction of entropy increase, stopping time would mean stopping entropy from increasing, freezing all physical processes at their current state of disorder, not permitting any further increase. But entropy increase is not a law you can pause. It is statistical. The molecules in a room are always moving, always colliding, always exploring the space of possible configurations. Stopping their motion would require reducing the temperature to absolute zero, which the third law of thermodynamics says is impossible. Every system above absolute zero has thermal fluctuations. Every system above absolute zero is producing entropy. Stopping time in the thermodynamic sense would require absolute zero temperature everywhere. And absolute zero is not just very cold. It is the lower bound that no system can reach, a limit that can be approached but never achieved. Time in the thermodynamic sense cannot stop. The arrow will always exist as long as the universe contains any energy. The question of stopped time runs directly into the question of absolute zero, and absolute zero is forever beyond reach. The fourth revelation: quantum mechanics has no pause button. At the quantum level, time has a different character. In quantum mechanics, particles do not have definite positions or momenta until measured. They exist in superpositions, spread across multiple possible states simultaneously, described by a mathematical object called the wave function that evolves continuously and deterministically according to the Schrödinger equation. The Schrödinger equation is a differential equation in time. It describes how the wave function of a quantum system changes from moment to moment. It is, in some ways, the most fundamental equation governing the behavior of matter and energy. The equation that underlies all of chemistry, all of material science, all of atomic and molecular physics. And the Schrödinger equation has a very particular relationship with time. For the wave function to stop changing, for quantum evolution to pause, for quantum time to stop, the right side of the Schrödinger equation would have to equal zero. This happens only when the wave function is in an energy eigenstate and the relevant terms vanish. For a system in a perfectly defined energy state, the wave function does not change over time except for a global phase factor that has no observable consequences. This is called a stationary state, and it sounds like time has stopped for that system. The observables, the quantities that measurements would reveal, do not change. Measure the system at one time or another. You get the same probabilities. But here is the crucial subtlety. The wave function is still evolving. The global phase is still rotating. The system is still, in a quantum sense, doing something. Its relationship to other systems is still defined. It can still be entangled. It can still be measured. Time has not stopped. The observable predictions have become static, but the underlying quantum state is still dynamic. There is a deeper problem with stopping quantum time. The uncertainty principle relates the energy of a system to the uncertainty in the time of its measurement. A system with a perfectly defined energy exists in a stationary state, but it must have been prepared in that state at some specific moment in the past, and the act of preparation required energy uncertainty during the preparation. The apparent timelessness of the stationary state is bought at the cost of temporal uncertainty in how it was created. More fundamentally, quantum mechanics operates in a universe with other systems. A system that is truly frozen in time, that cannot interact with anything, that cannot exchange energy or information with its environment, is a system that cannot be observed. The act of observation itself disturbs the system. The act of even knowing that the system is frozen in time requires some interaction with it, and any interaction destroys the frozen state. Quantum time cannot stop without also stopping the ability to know that it has stopped. Let us step back from the physics for a moment. There is a human intuition underlying the question of stopped time that goes back much further than modern physics. It appears in mythology, in literature, in philosophy. The fantasy of time stopping usually takes one of two forms. The first is the desire to pause good moments, to hold a beautiful experience in place forever, to prevent the loss that time inevitably brings. The parent watching a child sleep and wishing this moment could last. The traveler seeing a perfect landscape and wanting to stay in it. The lover wishing that this night would never end. The second is the fantasy of exceptional access, the power to freeze everyone else while you alone continue moving, perceiving, acting, to walk through a museum in perfect silence while the crowds are frozen mid-step, to read every book while the world waits, to have unlimited time in a world that is momentarily generous with it. Both fantasies reveal something important about what we mean when we talk about time. We are not just asking about physics when we ask about stopped time. We are asking about experience, about consciousness, about what it would mean to exist outside the normal temporal constraints. And physics has something to say about this too. The fifth revelation: consciousness requires time. We do not have a complete scientific theory of consciousness. The hard problem, the question of why there is something it is like to be a conscious being rather than simply complex information processing happening in the dark, remains unsolved. But we know a great deal about the neural correlates of consciousness, about what kinds of physical processes are associated with conscious experience. And all of them are temporal. Memory requires time. You cannot remember a moment that is not past. Anticipation requires time. You cannot anticipate a future unless there is a future. Perception itself requires time. Seeing an object requires light to travel from the object to your eye, which takes time. Sounds require time to propagate. Even the sensation of touch requires nerve signals to travel from the point of contact to the brain, which takes time on the order of a few hundred milliseconds. More deeply, the brain's processing is inherently temporal. Neurons fire in sequences. Patterns of activity propagate through neural circuits. Memories are encoded by changes in synaptic strength over time. The integration of sensory signals into a coherent perception of the world takes time. The sense of being in a present moment is itself a construction built from neural processes that unfold over roughly a quarter of a second. In the fantasy of stopped time, where you continue to exist and experience while everything else is frozen, you are imagining a situation in which you are exempt from the temporal cessation that has overtaken everything else. Your neural processes are still running, still creating experience, still building memory and perception and thought, while the physical processes of everything else are suspended. But if physics is really stopped, your brain's physical processes are stopped too. You are not exempt. You are made of the same matter as everything else. Your neurons are atoms. Your thoughts are electrochemical signals. If time stopped for atoms and electrochemical signals, it stopped for you. There is no version of physically stopped time in which an embodied consciousness continues. The fantasy of the frozen world observed by a free-moving individual requires a consciousness that is not physical, not implemented in matter, not subject to the laws that govern matter. It requires, in the most literal sense, a soul. Physics has nothing to say about souls, but physics does say this. If time stopped for everything, it stopped for you. There is no observer of the stopped universe. There is no one inside the pause noticing the silence. The freeze has no experiencer. And this means the question shifts. The interesting question is not what you would see if time stopped. You would see nothing, because you would not exist in any conscious sense. The interesting question is what the universe would be like in its stopped state, described from the outside if any outside could exist. And here physics has some extraordinary things to say. The sixth revelation. A universe without time is a universe without change, without cause, without meaning. In general relativity, time and space are not separate. They are dimensions of a single four-dimensional space-time. Events do not happen at a time and a place. They happen at a space-time location, a point in four-dimensional space-time. The history of the universe is not a series of snapshots in time. It is a four-dimensional structure, a block within which all events, past, present, and future, exist simultaneously. This is sometimes called the block universe or eternalism. All events are real. The dinosaurs are real, not in the sense that they exist now, but in the sense that they exist at specific space-time locations in the four-dimensional block. The Big Bang is real. The heat death of the universe is real. Every moment of every life that has ever been lived or will be lived exists in the block universe as a specific four-dimensional structure. In this picture, time does not flow. The experience of time flowing is a feature of consciousness moving through the block, of the mind's ability to access certain space-time locations as memories and others as perceptions, but the block itself is static. It does not change. It simply exists, all of it at once. In the block universe, asking what if time stopped makes little sense. The block is not in time. It is all times simultaneously. You cannot stop something that is not flowing. The block just is. But this creates a profound problem. In the block universe, why does time have a direction? Why does the four-dimensional block have a past direction and a future direction? Why does moving along the time dimension in one direction lead to lower entropy and the other to higher entropy? Why do causes precede effects? Why is there an arrow at all? The block universe gives you time's apparent flow as an illusion of consciousness, but it does not explain why the block has the asymmetric structure it has. Why is it different in one temporal direction than the other? The answer must lie in the initial conditions. The Big Bang began in a state of extraordinarily low entropy. That low entropy beginning broke the time symmetry of the laws of physics. Moving away from the Big Bang in one direction leads to higher and higher entropy. The future, moving toward the Big Bang, leads to lower and lower entropy. The past is the direction of lower entropy, and the block universe is not temporally symmetric because its boundary condition, its beginning, was not temporally symmetric. If you stopped time in the block universe, you would not be stopping something that was moving. You would be taking a slice through the block at a specific four-dimensional location. That slice is a moment, an instantaneous three-dimensional snapshot of the universe. and a snapshot is exactly what the block universe picture says every moment already is. The stopped time universe is just the block universe, with the instruction not to move along the time dimension. And in a universe restricted to a single temporal slice, there are no causes, there are no effects, there are no processes, there is no thermodynamics, no chemistry, no quantum evolution. Every particle is fixed in its position and momentum, frozen, precisely correlated with every other particle through the causal history that produced this particular configuration. But nothing happens next. Nothing has happened before. There is only the slice. This is what stopping time actually means, taken seriously in the physics of space-time. It means removing the temporal dimension from the structure of reality, leaving only a single three-dimensional snapshot. And that snapshot, without time, is not a world, it is a pattern, a mathematical object of enormous complexity but no dynamism, no story, no history, no future, just structure hanging in nowhere, meaning nothing to no one. Now let's think about what this all means for us, right here, right now, in this moment that already contains within it the entire mystery of time. The Voyager spacecraft, which we have explored in a previous video, have been traveling for nearly 50 years. Their plutonium power sources are decaying. Their instruments are being shut down one by one, their signals, crossing more than 14 billion miles of space, take more than 22 hours to reach Earth. They are dying slowly, inevitably, following the arrow of time in the direction of increasing entropy, the direction that all physical systems follow. Nothing about Voyager stops. Time does not pause for it, even in the extreme conditions of interstellar space. It ages, its atoms vibrate, its molecules interact, its radioactive nuclei decay. All of these processes are marks of time passing, of entropy increasing, of the universe's unidirectional arrow doing its inexorable work even in the cold dark of the space between stars. If time could stop for Voyager, none of these processes would occur. The radioactive decay, which is a quantum mechanical process with a rate that is determined by fundamental physics, would be suspended. The decay is not continuous, it is a series of discrete quantum events, each one a nucleus tunneling through a potential barrier and releasing energy. Stop time, stop the tunneling. Stop the tunneling, stop the decay. Stop the decay, and the power source that makes Voyager work is no longer decaying. But wait, the power source works by converting the energy of decay into electricity through thermoelectric generators. Stop the decay, and the electricity stops. Stop the electricity, and every instrument, every heater, every transmitter goes dark. Stop the transmitters, and the signal stops. Stop the signal, and the 22-hour journey of radio waves across 14 billion miles of expanding space-time ends in silence. In a universe of stopped time, Voyager is still there. Its physical structure persists, but it is doing nothing, sending nothing, experiencing nothing, being nothing in any dynamically meaningful sense. It is a pattern of atoms in a particular configuration, a three-dimensional snapshot of a moment in a spacecraft's life, held forever in a frozen instant that no instrument exists to measure and no consciousness exists to observe. Time stopping is not the universe taking a rest. It is the universe ceasing to exist in any sense that the word exist is meant to convey. Existence implies being, and being implies process, and process implies time. Without time, what remains is not the universe. It is the ghost of the universe, a static configuration that used to be dynamic and now is not, except there is no now, and the used to be has no meaning in a world without temporal succession. The seventh revelation. The deepest question is whether time is real at all. This is where physics, mathematics, and philosophy converge on something that most scientists do not discuss in polite company, but that serious thinkers have been wrestling with for decades. There is a problem in quantum gravity called the problem of time. When physicists try to combine quantum mechanics and general relativity into a unified theory of quantum gravity, the one they hope will describe what happens at the singularity of black holes and at the Big Bang, where both theories are simultaneously relevant, something extraordinary happens to time. In quantum mechanics, time is a parameter. It is the variable that appears in the Schrödinger equation, the thing with respect to which the wave function evolves. It is not itself a quantum observable. It does not have a wave function. It is the background stage on which quantum evolution unfolds. In general relativity, time is a dimension. It is part of the space-time fabric, shaped by matter and energy, varying from place to place and moment to moment. It is not a background. It is a dynamical entity that participates in the physics. These two roles for time are fundamentally incompatible. Combining quantum mechanics and general relativity produces, among other difficulties, the Wheeler-DeWitt equation, the central equation of canonical quantum gravity. And the Wheeler-DeWitt equation has no time in it, none. The equation that is supposed to describe the quantum state of the entire universe, including space-time itself, does not contain a time variable. The universal wave function does not evolve with respect to time because there is no external time with respect to which it could evolve. This is called the frozen formalism problem, or the problem of time in quantum gravity, and it is one of the deepest unsolved problems in fundamental physics. If the Wheeler-DeWitt equation is correct, then at the most fundamental level, there is no time. Time does not appear in the ultimate equation governing the universe. How then do we experience time? How does the time of our experience emerge from a timeless quantum gravity? The leading candidate explanation is called relational time or internal time. The idea is that time does not exist as an external parameter, but rather emerges from the correlations between different parts of the universe. Some degrees of freedom in the universe play the role of clocks relative to other degrees of freedom. We experience time as the relational structure of correlations between physical systems, not as a background parameter. In this picture, time is not a fundamental feature of the universe. It is an emergent phenomenon. It is what we call the pattern of correlations between physical systems when we describe the universe from within. At the most fundamental level, the universe is timeless, and time is what happens when a sufficiently complex subsystem of the universe describes the rest of the universe from its own perspective. If this is right, then time stopping is not just physically impossible. It is conceptually incoherent at the deepest level. There is no time to stop. There are only correlations between physical systems, and those correlations are the time. Stopping time would be stopping the correlations, which would be dissolving the very structure that makes the concept of time possible. There is a question that emerges from all of this that deserves careful attention. If time is emergent, as the relational time interpretation suggests, Then was there a time before time emerged? Was there a moment when the universe was timeless and then time began? This is the question of the origin of time, and it is one of the most profound questions in cosmology. Stephen Hawking, working with mathematician James Hartle, proposed what is called the no-boundary proposal. In their model, before the Planck time, the first 10 to the minus 43 seconds after the Big Bang, when quantum gravity effects become dominant, time was not a real dimension at all. It was imaginary in the mathematical sense, more like a spatial dimension than a temporal one. In this Hartley-Hawking framework, the universe has no beginning in time because time itself only emerged as the universe cooled below the Planck temperature. Before that, or more precisely at the Planck era, there was no before. The question of what happened before the Big Bang is like asking what is south of the South Pole. The geometry of the situation makes the question meaningless. The universe did not begin at a moment in time. Time is part of what the universe began with. The universe and time emerged together as one package from whatever quantum gravitational state preceded the hot Big Bang expansion. If this is right, then time stopping could in principle happen if the universe were to return to a Planck-scale quantum gravitational state. In the interior of a black hole, approaching the singularity, the density approaches Planck density and the curvature approaches Planck curvature. Quantum gravity becomes essential. And in that quantum gravitational regime, time as we know it may dissolve, not stop in the sense of the arrow pausing, stop in the sense of ceasing to be a real temporal dimension, becoming instead another spatial-like direction, losing the distinction between past and future, becoming geometrically equivalent to space. This is time stopping in the most radical sense. Not a pause, but a dissolution. Time does not continue in another form. It ceases to be time. And this may have already happened. In every black hole that has ever formed, the matter falling toward the singularity may be entering a regime where time dissolves. We cannot observe it from outside. The event horizon seals whatever happens inside from any external communication. The physics of time dissolution may be occurring right now in the deep interiors of the black holes at the centers of galaxies, hidden from any possible observation. The universe may already contain regions where time has stopped. Not because it paused, but because it dissolved into something geometrically different. And we would never know. Let's talk about what all of this means for the human experience of time. Because the physics of time and the psychology of time are connected in ways that are rarely discussed. The human brain does not experience time as a uniform flow. Psychologists have documented that time seems to pass slowly when we are bored or frightened, and quickly when we are absorbed or happy. Extreme fear can make a few seconds feel like minutes, as the brain floods with stress hormones and processes information at an elevated rate, creating a denser record of events and a subjective sense of more having occurred. Meditative states can create a sensation of time, slowing to the point where the ordinary succession of moment to moment becomes less salient. Advanced meditators report experiences in which the sense of being located in a particular temporal instant becomes less fixed, where the boundaries between past memory and present perception become porous. None of this is time actually slowing in a physical sense. A physicist with a precise clock monitoring a meditating monk would find no deviation from normal clock rates. But the subjective experience of time, the felt sense of duration, is not the same as physical time. Consciousness constructs its temporal experience from neural processes, and those neural processes can be modulated by chemistry, attention, emotional state, and practice. The fact that our experience of time is constructed, that it is a representation built by the brain from physical signals rather than a direct perception of an objective temporal flow, connects to the deeper physics we have been discussing. If time is relational and emergent rather than fundamental, if it arises from correlations between physical systems rather than existing as an independent backdrop, then the brain's construction of experience time is not so different from what the universe does at the most fundamental level. Both the brain and the universe, in this picture, create their temporal experience from correlations between physical processes. The brain creates the experience of now from the integration of neural signals over a quarter of a second. The universe creates the experience of time from the relational structure of correlations between physical systems over cosmic scales. If time stopped physically, the neural correlations that create temporal experience would stop. The constructed now would dissolve. Experience would not just be frozen, it would be gone. Not because consciousness escaped, because the physical substrate of consciousness, the correlations between neurons that produce the integrated experience of a moment, would be frozen too. The experience of the frozen moment does not persist. The frozen moment is precisely the cessation of experience. One more thing deserves attention before we close. The heat death of the universe, which we explored in a previous video, is the state of maximum entropy in which no further thermodynamic processes are possible. In that state, the arrow of time loses its meaning. Not because time stops in a dramatic sense, because there is no more entropy to increase. No more disequilibrium to drive any process. Every region is in equilibrium with every other region. The future is indistinguishable from the past because neither contains anything the other does not. In the heat-death universe, asking which direction is the future is like asking which direction is up in the middle of the ocean when the water is perfectly still. Up and down are defined by gravity. Future and past are defined by the entropy gradient. Remove the gradient, and the distinction dissolves. The heat death does not stop time in the sense of halting a flowing process. It removes the asymmetry that made the concept of time's direction meaningful. Time continues in the sense that the four-dimensional block still exists, that the particles still have their positions and momenta, that the universe still occupies its space-time volume, but nothing distinguishes the time direction from any other direction. The universe becomes, in a thermodynamic sense, isotropic in time. Future and past look the same. This is the closest the universe gets to stopped time without requiring impossible physics. Not a halt, a dissolving of the feature that made time directional. The arrow of time does not break. It simply runs out of something to point at. And this is not a speculation. This is where the universe is going, with the certainty of the second law of thermodynamics, over time scales that make the current age of the universe look negligible. The universe is spending its temporal arrow, converting the low entropy of the Big Bang into the high entropy of the heat death. one irreversible process at a time. The heat death is time's retirement, the point at which the universe no longer has anything for time to do. What does all of this mean? We began with a question that sounds simple. What if time stopped? And we discovered that the question is anything but simple. It is a lens that focuses some of the deepest problems in physics into a single point of inquiry. We found that time already stops for photons, that relativistic time dilation is real and measured and produces zero elapsed time for massless particles at the speed of light. We found that near black holes, time nearly stops, and at singularities, it may dissolve into something geometrically different from time. We found that the arrow of time comes from entropy, and that stopping entropy increase would require absolute zero temperature, which is thermodynamically impossible. We found that quantum mechanics has no pause button, that quantum evolution is continuous and cannot be suspended without destroying the system. We found that consciousness requires time and that a universe of stopped time is a universe without any experiencer of the stopping. We found that in the block universe picture, time stopping means reducing existence to a single three-dimensional slice with no dynamics, no cause, no effect, no meaning. And we found that at the deepest level of quantum gravity, time may not be fundamental at all, may emerge from correlations between physical systems rather than existing independently, making stopped time not just physically impossible, but conceptually incoherent at the foundations. 7 revelations, each one dissolving a different aspect of the intuition we brought to the question. Time is not a river that can be dammed. It is not a clock that can be stopped. It is not an external parameter that can be paused. It is, depending on which level of physical description you are working at, a dimension of space-time, an emergent property of entropy gradients, a relational structure of physical correlations, or the direction in which quantum states evolve. Each description is valid at its level. Each makes stopping time either impossible or incoherent. What we experience is time, the felt sense of being in a moving present, of remembering the past and anticipating the future, of existing in a now that is continuously slipping away into the past as new nows emerge, is a construction built by neural processes, grounded in physical correlations, ultimately rooted in the extraordinarily low entropy beginning of the universe that pointed the arrow. We did not choose to exist in time. We are what time does when matter organizes itself into sufficient complexity. We are the universe's way of having a temporal experience of itself, the part of the cosmos that not only moves through time but notices that it is moving, wonders where the movement comes from, asks what would happen if it stopped. Asking what if time stopped is one of the most fundamentally human questions. Not because it has a practical answer, it does not. Not because it can be experimentally tested, it cannot. But because it forces us to examine what time actually is, rather than what we unreflectively assume it to be. And when we do that, when we really look at what time is in the light of everything physics has learned, we find something that is simultaneously more fragile and more extraordinary than we imagined. Time is not given. It is not guaranteed. It emerged from a particular kind of universe with a particular kind of beginning. It is maintained by the ongoing decrease in order that has been proceeding since that beginning. And it will eventually, over spans of time that dwarf our imaginations, lose the asymmetry that makes it a direction rather than just another dimension. We are living in time's bright chapter, the era when entropy is actively changing, when processes are ongoing, when causes are producing effects, when the future is genuinely different from the past, the era when time means something. The question is not what if time stopped. The question is, what does it mean that it has not stopped yet? That right now, in this universe, at this moment, time is still doing its work, still carrying the universe from its low entropy past toward its high entropy future, still building the structure of before and after that makes experience possible, that makes memory possible, that makes the asking of questions possible. Still giving you a now in which to wonder about what would happen if you lost it. That is a gift the universe is giving you, one irreversible moment at a time. And the physics of time makes clear how extraordinary that gift is. Not because time is infinite, it is not. Not because time is guaranteed, it is not. But because in a universe where the most fundamental equation of quantum gravity has no time in it, where the laws of physics are time-symmetric, where photons already live without it, time has somehow emerged, has somehow persisted for 13.8 billion years, has somehow produced the conditions for beings who can ask about it. We are the universe noticing that it is in time, noticing the arrow, noticing the flow, wondering what it would be like to step outside. And physics says, you cannot step outside. There is no outside. Time is not a container you are in. Time is something you are made of. Stop it and you do not survive to notice the silence. All you can do is what you are doing right now. Move through it. Notice it. Pay attention to the particular shape of this moment, because this moment, this slice of the four-dimensional block, is the only moment you occupy. The past is gone. The future has not arrived. There is only now. And now is the most extraordinary thing the universe has ever produced.